Hello all. In this video we will take a closer look inside the mirror space. The geometry of the mirror space is entirely determined by the properties of the phi function that we have seen so far. Still, under some assumptions, there are some common properties that can be related to certain other properties in the Euclidean space. Let us look at the properties of the Bregman divergence. It is given by d phi of x comma y equal to phi of x minus phi of y minus gradient phi of y comma x minus y. We are assuming that the phi function is mu phi strongly convex. Observe the following properties. The first property is that asymmetry, which is that d phi of x comma y is not the same as d phi of y comma x. So that's why we are not calling it a distance but a divergence. The second is the non-negativity. Since mu phi is strongly convex, if we use the quadratic lower bound property on phi, it would imply that d phi of x comma y is greater than equal to mu phi by 2 times norm square of x minus y. Which means that d of x comma y is always non-negative because the lower bound is a non-negative number. Another implication of the strong convexity of phi is arising from another property that we have seen in the context of strongly convex functions, which is that d phi of x comma y is less than equal to 1 by 2 mu phi times dual norm square of gradient phi of x minus gradient phi of y. So this property will be very useful later on. Finally, note that d phi of x comma y is also strongly convex in x because phi is strongly convex in x. There is a somewhat famous inequality known as the Pinsker inequality for probability mass functions, which says that the KL divergence between x comma y is greater than or equal to half of L1 norm square of x minus y. The proof is a bit lengthy, so we will not look at it, but an implication of the Pinsker inequality is that the phi function, which in this case is the negative entropy, is one strongly convex with respect to the L1 norm. Note that within the mirror descent framework, all norms should be compatibly defined. So in this example, since we are taking mu phi equal to 1, that means that our norm of interest is L1 norm. So when we are considering Lipschitz continuity parameter, we have to consider the corresponding dual norm on the subgradient. That is, we need to require that dual norm, which is infinity norm now. So GT infinity norm is less than or equal to LF. So in other words, the KL divergence based mirror descent is well suited to scenarios where the infinity norm of GT, the subgradient, is not too large. To develop further intuition, let us take a ride into the mirror world. Then the update can be written as xt plus 1 equal to argmin over x in calligraphic x inner product of gt comma x plus 1 by eta t d phi of x comma xt, where I have removed some of the constant terms. Now this can be written as argmin over x in calligraphic x inner product of eta t gt minus gradient phi xt comma x plus phi of x. This can equivalently be written as arg max of x in calligraphic x inner product of gradient phi xt minus eta t gt comma x minus phi of x. For a moment, ignore the domain restriction calligraphic x. Then this should remind us of the definition of the conjugate of phi. In fact, if you recall the conjugate subgradient theorem, it said that inner product of u comma v is equal to phi u plus phi star of v, where phi star is the conjugate of phi. This is equivalent to v equal to gradient of phi at u, which is equivalent to u equal to gradient of phi star at v. Here we are using gradient because we have assumed that phi is smooth. then comparing with the update, we can see that the optimality condition is equivalent to gradient phi at xt plus 1 equal to gradient phi at xt minus eta t gt. This can also be written equivalently as xt plus 1 equal to gradient of phi star of gradient phi of xt minus eta t gt. So intuitively, the mapping gradient of phi takes xt from ambient space to the mirror space. There we take the gradient step, and then the mapping grad phi star takes us back to the ambient space. You can see that if we vary eta from 0 to some value, then the next iterate will be on this straight line in the mirror space. But in the Euclidean space, that straight line may correspond to some curve. So this is the basic idea of mirror descent algorithm. Of course, here we did not have any constraints. So once you go into the mirror space, you can also stay there and carry out multiple iterations and then come back at the end. So that would be another way of implementing the mirror descent updates if you don't have any constraints. If there are constraints, it brings us to the notion of Bregman projection. In the general case, there is a slight problem with the intuition presented earlier. Specifically, it is that the set calligraphic X is only defined for the ambient space, which was an inner product space. We do not have a counterpart of calligraphic X in the mirror space. So the projection operation cannot be carried out in the mirror space. Let us define yt plus 1 as gradient phi star of gradient phi of xt minus eta t gt. So this is the point where the iterate was supposed to be had there been no constraint. So in the classical case, we are finding a point xt plus 1 in calligraphic X that is closest to yt plus 1. But that is not really a good idea here because the standard projection operation uses norm square as a distance metric in order to find out which point is the closest. But in this case, all our distances have been replaced with Bregman divergences because our notion of which 2 points are near and which 2 points are far is different and is based on the Bregman divergence. So we cannot use the standard projection here. In other words, we want to find a point in calligraphic X that is closest to yt plus 1, but at the same time, that closeness metric has to be the Bregman divergence. So the Bregman projection operation is defined as px phi of x equal to argmin over u in calligraphic X d phi of u comma x. And the actual updates are given by xt plus 1 equal to px phi of yt plus 1. So here px phi denotes the Bregman projection operation. So this is the intuitive argument for Bregman projection. Although we have argued the Bregman projection makes sense intuitively, it is actually also implied by the form of the mirror descent updates. To see this, recall that we wrote the updates as xt plus 1 equal to argmax over x in calligraphic X, inner product of gradient phi of xt minus eta t gt comma x minus phi of x, whose optimality condition can be written as gradient phi of xt minus eta t gt minus gradient phi of xt plus 1 comma z minus xt plus 1 is less than equal to 0 for all z in calligraphic X. Now we also defined yt plus 1 equal to gradient phi star of gradient phi of xt minus eta t gt. So gradient of phi at yt plus 1 is equal to gradient phi at xt minus eta t gt. Then the optimality condition can equivalently be written as gradient phi of yt plus 1 minus gradient phi of xt plus 1 comma z minus xt plus 1 is less than equal to 0 for all z in calligraphic X. But this condition which we have written is exactly the optimality condition of xt plus 1 equal to px phi of yt plus 1, which is equal to argmin over u in calligraphic X d phi of u comma yt plus 1. So this is because gradient of d phi at u comma yt plus 1 is equal to gradient of phi of u minus gradient of phi at yt plus 1. So we have established that the Bregman projection operation is consistent with the mirror descent update that we wrote down earlier. Coming back to the figure that we have seen earlier, suppose that we are at a point xt, then the mapping grad phi takes us to the mirror space, where we then take a step along the negative gradient direction. After that, grad phi star takes us back to the Euclidean space, which is the point yt plus 1. Then to find a point in calligraphic x that is nearest to yt plus 1, we search a point that is closest along this curve defined by d phi of x comma yt plus 1. Note that if we are measuring in the Euclidean space, the distance between yt plus 1 and xt plus 1 is not the smallest, but it is only smallest along this curve, or equivalently it is only smallest in the mirror space. So this kind of curve is called the geodesic. We cannot directly carry out the projection in the mirror space, since calligraphic x is only defined for the ambient space. So with this, I hope the intuition for mirror descent is clear. In order to analyze mirror descent, however, note that we need some more properties. Since the Bregman divergence is not a distance metric, there are some fundamental issues that need to be resolved in order to even begin the analysis. The first issue is that in the Euclidean space, we have a well-defined notion of angle, which led to certain properties for projections such as the angle property. But we do not have angles in the mirror space, so we need some kind of other inequality in its place. Let us look at the result called the generalized Pythagorean, which is the counterpart of the angle property for the projection operation in the Euclidean space. Recall that the angle property said that the angle between x minus px of x and z minus px of x for z in calligraphic x was always obtuse. This was the optimality condition for the projection operation. We want to express this result without using the notion of angles at all. Consider the triangle formed by the points z, x and px of x. Whenever we have a triangle which is obtuse, the Pythagoras theorem says that norm square of z minus x is greater than or equal to norm square of z minus px of x plus norm square of px of x minus x. The same kind of thing can actually be written for Bregman divergences, and this is called the generalized Pythagorean, which is that d phi of z comma x greater than or equal to d phi of z comma px phi of x plus d phi of px phi of x comma x for all z in calligraphic x. So in order to formally prove it, we first observe the following equality, which is that inner product of gradient phi of y minus gradient phi of x comma z minus x equal to d phi of z comma x plus d phi of x comma y minus d phi of z comma y. So this is called the 3-point lemma, and it can be directly derived by just substituting d phi and expanding. So let us come to the proof. Let us denote x phi as px phi of x for the sake of brevity. Then x phi is equal to argmin over u in calligraphic x d phi of u comma x. And the optimality condition of this operation can be written as inner product of gradient phi of x phi minus gradient phi of x comma z minus x phi greater than or equal to 0 for all z in calligraphic x. Then applying the 3-point lemma to the term on the left, we obtain that 0 is less than or equal to inner product of gradient phi of x phi minus gradient of phi of x comma z minus x phi, which is nothing but minus d phi of z comma x phi minus d phi of x phi comma x plus d phi of z comma x, which is the required result. The generalized Pythagorean gives rise to the property called quasi-non-expansiveness property. So the generalized Pythagorean says that d phi of z comma x is greater than or equal to d phi of z comma px phi of x plus d phi of px phi of x comma x. Now all the divergence terms here are non-negative. Therefore, we can drop one term from the right and the inequality would still hold, and therefore rearranging we obtain that d phi of z comma px phi of x is less than or equal to d phi of z comma x for all z in calligraphic x. So in other words, the distance of z from the projected version of x is always less than or equal to the distance of z from actual x, so long as z belongs to calligraphic x. This inequality is somewhat similar to the non-expansiveness property of the projection operation. It is, however, a weaker condition since we require z to be in calligraphic x. So this is called the quasi-non-expansiveness property of the Bregman projection. So with this, we are done looking at most of the properties of the Bregman projection and the rules of operating in the mirror space. In the next video, we will start analyzing the oracle complexity of mirror descent.